When checking my own video about the custom IK solver using Maya nodes, I realized I left out one optimization we could still do to make it a little bit faster. So when we have the IK solver setup in the node editor, when we have the triangle and the sides A, B and C and the angle B, for the upper part, everything is fine as it is. If we look at the nodes right here, we're using the law of cosines to get the cosine value. So basically, this part is doing the law of cosine. So recapping, the cosine of angle B equals A squared plus C squared minus B squared divided by 2AC. So the square of the lower, or the A and B, and let's see, where is the other? Here. So the length, this is the C squared, it's the arm length, the current length. So the upper part is all nice and well, but for the lower arm segment, we are doing the same thing. We're using the law of cosines to solve for the angle of C. So the C angle, capital C, and this is lower C. And we're doing the same thing here. We're using the cosine of angle C is A squared plus B squared minus C squared divided by 2AB. And that's what we're doing here. We're doing the non-plus, so the A squared plus B squared. We're subtracting the C squared. And then we have the numerator, the upper part of the equation. And then for the lower part, the denominator, we have the 2 value, and we add the AB values to it. So it's the upper and lower length of the arms. And then the result is the cosine value of the angle. And what we then went on to do is we used the arc cosine node to get the angle. And then, because in the straight arm situation, the angle for the solver is 180 degrees, because it is a straight line, and that's an angle of 180. And in our setup with nodes, it should be an angle of 0. So we subtracted the angle from 180, so basically rotating it 180 degrees. And then, because we didn't want it to arc the wrong way, we negated that angle. And then with this new angle, we used a sine node to get the sine value to construct the rotation matrix. But if we look at this in more detail, what's happening, so let's clear this out. If we look at the unit circle, where we have a vector that gets rotated, and the vector at this point is rotation angle 0, so the cosine is 1. So the cosine is the horizontal axis, and the sine is 0, so the sine is the vertical axis. And if we have, for example, rotation of 135 degrees, we end up somewhere here, and this is basically the sine value, and this is basically the cosine value. So what happens when we subtract 180 from this angle, or rotate it 180 degrees, we end up with a rotation vector that's here. And what that basically does is just say, okay, take the cosine and we negate it, and we take the sine and we negate it as well. So if we take the negative sine and the negative cosine, we end up right here. And if we then were to, what we do here, negate the angle again, so this is, let's say, negative 45 degrees, and if we negate that, we get a rotation of positive 45 degrees. And basically what that is doing is just negating the sine value again. So we end up with the original sine value and the negated cosine value. So all we have to do to get this 180 degree rotation and then negated rotation is only negate the cosine value. So all the nodes that I used in between here, the arc cosine, the subtract node, the negate node, and the sine node, are all well, not needed, because we can use the Pythagorean theorem to get the sine value, and then we can use that to plug directly into the matrix construction node. And the cosine we already have, and we're already using the negated cosine value, so it's just the sine value that we calculate with these nodes, and we can do that in a quicker way, because now we're using an arc cosine and a sine, which can be more expensive than using the nodes for the Pythagorean theorem. So let's do that now and set this up in a little bit quicker way. So to use the Pythagorean theorem, we're going to do the same thing as before. We have a right-angled triangle, and we have the hypotenuse, which is of length 1, and we have the cosine value, let's call it A, and we need the sine value, let's call it B, and the hypotenuse is always C, so A squared plus B squared is C squared. So in this case, if we do C squared, which is still 1, because 1 times 1 is 1, and then subtract the squared cosine value, we get the squared sine value, and if we take the square root of that, we get the sine value back again. So let's create a multiply node and plug in the cosine value twice, and then we do a subtract node, and we set the first input to be 1, because that's the squared hypotenuse. And then we plug in the squared cosine value into the second input. Now we have the squared sine value. And now we can take the square root using the power node, setting the exponent to 1/2. And then plug in the squared sine, and now we have the sine value. And in the same way we had the sine value here in the old situation, we can reuse the negation node and plug it directly into here. And because in this situation we already negated the angle here, and then we did a negation on the sine again, the plugs need to be switched, because we're only doing one negation of the sine value here. So this should go into the connection where the sine value went in, and then the sine value that's not negated should go into the x component of the basis vector y. So the negated sine value goes into the y component of the basis vector x, and the not negated sine value goes into the basis vector y x component. And now you can see, if we clear our view and we take our IK handle, that the IK is working again, and we saved ourselves some nodes. However, if we now stretch our IK beyond its maximum length, you'll see that the locators again disappear, because if we look at our sine value, we see again not a number value, which is produced by the power node, because we again have a negative zero number, so a very small number that's just a little bit below 0. To prevent this, again, we can use the maximum node to clamp it at 0. So we use a max node again, and then we create a float constant node, set the value to 0, and then we take the maximum of 0 and the squared sine value, and now we have a value that never goes below 0, and if we plug that into the square root node, and select the locators to make them visible again. If we now manipulate our AK handle, they still stay visible, and we do not have the not a number value anymore. So we fixed that in the same way we did before. So let's just rename these nodes for now. Okay, so I renamed them to the cosine value squared, and then the sin value squared, where we subtracted the cosine value squared from the 1, so we get the sine value squared. And then we the maximum node I renamed to sine squared clamped, and then the square root node, or the power 2.5 node, you renamed them to the IK sine. And then we can remove these 4 nodes because we're not going to use them anymore. So we replaced 4 nodes with 4 nodes, but cheaper 4 nodes. So in the end, this will be faster. And now we're back to our working IK solver, but just a little bit quicker than before.